Today, class, we're going to look at the effect of vapor pressure in solutions. So remember, a solution is when we're mixing two things together without a chemical reaction. Okay, so they're literally just mixing together. Okay, so what happens to vapor pressure when you have a solution? So when you do mix something. Okay, when does this possibly come important? That'll be like when we're putting ice on the roads. Today is a snow day. Okay, so why do we put ice on, not ice, let's put ice on the road. Why do we put salt on the road? And the reason is because now we're mixing ice with salt, okay, which is like water and salt. So you have a solution, and that new solution is going to have a new vapor pressure. Okay, so let's see. You can calculate the effect of vapor pressure with what's called Raoult's law. Okay, now recall that vapor pressure is basically a measure of how volatile you are. Okay, so if I come over here, you have a beaker here, and you have your gas, and this is closed system, so there's a lid on here. Here's a lid. Okay, and you have a liquid, and you have a gas, and the gas is basically evaporating up here spontaneously on its own. Okay, now the gas up here, these molecules, causes this pressure. Okay, and the pressure, the amount of pressure, if you actually measure this is called the vapor pressure. Okay, so it's the gas that's causing this pressure. Okay, now the more gas molecules you have, the higher the vapor pressure. Okay, so basically it's more volatile, meaning you have more gas molecules. Okay, so that's vapor pressure. So basically it is the pressure of your gas at dynamic equilibrium. So the rate at which condensation and evaporation are happening at the same time. So again, if you had a closed system, okay, you put a lid on there and you measured the pressure of the gas, that would be the vapor pressure. Okay, and again, the higher the vapor pressure, the more volatile, the more easily you become a gas. Okay, which makes sense again because if you have a higher pressure, that means you have more molecules up here, more gas molecules, so that obviously means it was easier to become a gas. Okay, so that's vapor pressure. So let's look at the effects of it. So what we're going to do is here's the formula. Let me go ahead and just write that down. So the new pressure of the solution equals to the mole fraction of the solvent. Notice this is the solvent, okay, multiplied by the pressure of the solvent, so the pure solvent. Okay, so this will give you the new vapor pressure once you mix something in there. So let's look at this. Calculate the vapor pressure at 25 degrees Celsius of a solution containing 99.5 grams of sucrose. Okay, so that's salt. So we have sucrose equals 99.5 grams. And we have 300 mils of water. That's our solvent. H2O is 300 milliliters. So this is our solute. That's what we're mixing in there. This is our solvent, the one doing the dissolving. And the original pressure of pure water is 23.8 torr, and the density of water is 1 gram per milliliter. Okay, so pressure of the solvent of water is 23.8 torr. Okay, and the density of water is 1 gram per milliliter. Okay, so let's see what we have here. Do we have the pressure of the solvent? Yes, right here. Let me change the color. We have that right here. Okay. Do we have the mole fraction? Not yet. Remember, the mole fraction is the part in moles over the whole. whole. So this is mole of the solvent. That's the part. And the whole is the total moles. Okay, so we need to calculate that. We have milliliters of the solvent, but we don't want milliliters, we want moles, okay? So how can I get this to a mole? Well, look what I have here. I have the density of water is 1 gram per 1 milliliter. So I'm going to use that. I can put milliliters on the bottom to cancel it out. 1 gram, okay? But do I want grams? No. I want moles. So remember, to go to a mole, you go the gram at the bottom to cancel out, moles on top, so you use the molecular weight. Anytime you go from a gram to a mole, always molecular weight. So water weighs, we'll say molecular weight of water, H2O, is 18 grams per 1 mole. Okay? So we would put 18 grams per 1 mole of water. Now when I multiply this out, I'm going to have the moles of water, which I have calculated at 16.67 moles, and that's of my solvent. Okay, so I have my moles of solvent. I don't have my total moles yet. I need to get my moles of my solute. Okay, so let's do this. Let me bring it down here. I have 99.5 grams of sucrose, okay? But remember, how do I go to a mole? Because I want moles. I use the molecular weight again, just like I did up here, okay? The molecular weight of sucrose is 180 grams per mole. And I got that by just adding up the formula of sucrose, okay? So I'm going to get, if I go 99.5 divided by 180, I get 0.55 moles. This is of my solute. Okay, so now I can do my mole fraction. So if I put my mole fraction here, and this is of my solvents, so that means I want my solvent on top. I have 16.67 moles of solvent divided by the total moles. So the total moles are 16.67 plus my solute 0.55. So the total is when you add all of them together. Okay, so when you do this divided by this added together, my mole fraction then becomes 0.97. So that basically tells me that 97% of the solution is water, okay? But not 100%. So since it's not 100%, if it was 100%, then the vapor pressure would be 23.1 or 23.8, right? Because then this would just be 1. Okay, but it's not. So let me get a different color here. Let me get this light blue. So my new pressure of my solvent, or my solution equals to my mole fraction, which I found right here, 0.97, and then my original vapor pressure, which was 23.8. So 0.97 right here, 23.8 right here. Okay, so basically this says I don't have 100% of water now. I only have 97% water. So what is my new vapor pressure, since it's not all water? And that would be, let's see, 23.1 torr. Okay, so what happened here? I put in a non-volatile substance, so basically like a solid is usually what you're using. I put a solid in there, and what happened to my vapor pressure? It was 23.8, and now it's 23.1. Do you see that it lowered? So I lowered my lower vapor pressure. Okay, so if I have a lower vapor pressure, that means I have less gas molecules up, in the gas phase. So what does that mean? That means it's less volatile, meaning it's harder to evaporate now. Okay, this increases the intermolecular forces, harder to evaporate. So we'll say less volatile, okay, which means it's harder to evaporate or to become a gas. Okay, so what are some of the consequences of that? We're going to do another example of this. File, new. Okay, this, when you have a lower vapor pressure, this means you're going to have a higher boiling point. That means it's harder to become a gas. Okay, and you're going to have a lower melting point. Okay, so if we think of this in terms of salt on the road, okay, so the ice, right? Okay, or sorry, not lower melting point, lower freezing point. That would make way more sense. Okay, lower freezing point. So let's think about this. We have a road. Okay, we put some salt on here. Okay, and we do this because we don't want ice. Okay, why? Because we're lowering the freezing point of ice. So what happens if we lower the freezing point? It makes it harder to form solid. Because a freezing point is when you're making a solid, so that means it's harder to form your solid, or in this case, your ice. It's harder to form your ice because you have to have a lower temperature. Okay, so instead of, we all know the temperature, 32 Fahrenheit. We're always looking for our snow days, okay? Well, if you put some salt on there, maybe the temperature to freeze water now is not 32. Maybe it's more like 30, okay? So now the roads have to get down to a lower temperature for the ice to freeze. And so that's why you do it. It's all with solutions here. Okay, so let's do another calculation. So let's look at, before we were looking at sugar, which is, what's the word? It's a covalent molecule, okay? But let's look at an ionic molecule. What happens if I put like a salt on there? Well, when you have a salt, it breaks up into ions, charged particles, okay? And so it has more an effect. So for an example, NaCl, sodium chloride, will have twice the effect because it's going to break up into 2 ions. You see there's 1 sodium, 1 chlorine. Sodium nitrite will have 3 times the effect because it's going to form 3. Do you see 2 NOs and 1 Ca, calcium, okay? So you're going to form 3 times as much. So let's look at this in action. Okay. In a solution, so it's the same formula, except now we're having an ionic compound instead of a molecular one. Okay, so a solution contains 0.102 moles of calcium nitrate. Okay, so we have 0.12 moles CaNO3. 2. Okay, remember, P of the solution equals to mole fraction of the solvent times pressure of the pure solvent. Okay? So we have moles, so this is going to go into our mole fraction here. And 0.927 moles of water, so I have 0.927 moles of water. This is our solute. This is our solvent. Okay. Calculate the new vapor pressure. The vapor pressure of pure water is 118.1 torr. So pressure of the solvent equals 118 point, was it 0.3? Let me make sure. 0.1 torr. And this is at 55 degrees. So instead of 25. So this is a different temperature. That's why the pressure is different. Okay, so we have the, here we go. We have the pressure of the solvent, okay? But now we need the mole fraction here. Now this is where, since I have a ionic compound here, so the solvent is ionic, I know this because I have a metal and a nonmetal, you now have to multiply it by how many ions it could break up into. So do you see NO3, how many of those do I have? I have 2 of those. Okay, plus how many calciums? 1. So this could break up into 3 ions, or it will break up, I should say, into 3 ions. So now let's put that into consideration into our mole fraction. Okay, so our mole fraction is going to be moles of solvent multiplied by moles of solute, or divided by, sorry, plus mole of solvent, so basically the total. Okay, so we have our moles of our solvent, that is 0.927. Our moles of our solute is 0.12, okay, plus moles of our solvent, again, because we want the total. Now here's where it's going to change a little bit, okay, because, well, we have 0.12 moles of that, but it's going to break up into 3, so we have to multiply this right here by 3. Okay, so the solute molecules by 3 because it's break up into 3. So this is kind of like the new number you need to add in if you have an ionic compound. So if it was NaCl, for example, you see you have 1 sodium, 1 chlorine, so you would have put a 2 right there. Okay, so if you do this, you multiply and divide it all out, you will get, let's see, 1.75 approximately. So this is my mole fraction, 0.75. Okay, so now we change the color again, or let's go here, and let's find the new vapor pressure of the solution. Okay, so now before I had 100% water. Now I only have 75% water. Okay, now I need to multiply it by the vapor pressure of the pure water, which is 118 from right here. Okay, so now since I only have 75% water instead of 100%, what is my new vapor pressure? And you multiply that out and you're going to get 88.8 torr. Okay, so again, do you see that an ionic compound, since it's going to break up into ions, you have this new kind of multiplication factor here, so it has more of a dramatic effect on the vapor pressure. Where before it only went down, I believe, 0.7 torr, okay, which is almost nothing, but it is something. But look how far this went down. It started out at 118.1 and it went down to 88.8. That's way more dramatic. So an ionic compound will always have more of an effect. And we usually use the word salt, okay? And so adding a salt or ionic compound to a solution will always lower the vapor pressure even more. Okay, so that's how you can kind of calculate the effects of vapor pressure by adding a solute to it. Here's sort of what I've been saying, okay? So the pink here, this is like a way of saying the vapor pressure. So here's the pressure over here on the y-axis, and here's the temperature, okay? Now when I add a solute to it, do you see now I get this blue line? So this is the new vapor pressure, okay? So if this is the freezing point, okay, do you see the temperature down here went all the way, it went lower, and the boiling point, we'll say, is up here, okay? Now the boiling point is over here. Anyway, so it's an interesting thing to look at. So basically, you're going to have a lower freezing point and an elevated boiling point. And so in the next slide, you're going to do this. You're going to look at, well, what effect does it have on freezing point? What will the new freezing point be? And if we look over here, what is the new boiling point? Okay, so we'll go through those examples. This one here, just know that when you put a solute into a solution, you're going to affect the vapor pressure. You're always going to lower it, which causes the freezing point to lower and the boiling point to increase. This is also why you put ethylene glycol into your engine, right? So the engine fluid, because you don't want your car to overheat, for example. So yeah, remember, if you put something into the solution, so we put some antifreeze in there, okay, so that's going to make the boiling point higher, so it won't overheat. But at the same time, it allows the solution not to freeze because it lowers the freezing point. It does both. It'll always do both. And so that's the reason you put antifreeze or ethylene glycol into your car. Anyway, I hope you find this interesting.